Good morning, everyone.
Good morning, Professor Vivo.
Good morning, Professor Malakar. So, today is our fourth day of faculty development program sponsored by ATAL, AICT. So, today we have an interesting talk by Professor Malakar. So, we'll start. Before we start, I should read the short CV, a short biography of Professor Malakar. Dr. Chandi Charan Malakar is completed his master degree in chemistry at Indian Institute of Technology, Kanpur in 2006. Then he obtained PhD degree in 2011 from University of Wenham, Stuttgart, Germany, under the guidance of Professor Wei Baifus. After successive postdoctoral research with the Professor K. Tehrani at the University of Antibes in 2011 and 2012, Professor Antipu Humchen at Rupchet Karl University, Edinburgh from 2012 to 2014, and Professor P.S. Mukherjee at IIC Bangalore 2015. Then he has a couple of industrial experience from 2014 to 2015 at this as a senior principal scientist at Sigma Chem Life Science Private Limited. He started his career at National Institute of Technology, Jalandhar, as an assistant professor in July 2015. Then Dr. Malakar moved to National Institute of Technology, Manipur in October 2015 and currently working as a assistant professor. He received several awards such as BOF Postdoctoral Fellowship from Belgium, ACRB Yearly Research Award, then Core Research Granted, and all these fellow from GAN MHRD, Government of India, as a course coordinator. He also experienced in several administrative positions in NIT Manipur as a TQ coordinator, then associate dean in research and consultancy, head of the department, chief warden, and several. So he has published more than 70 research articles in peer-review international journals, mostly on the pharmaceutical nanomaterials. And his current research interest in CH activation, uh, in active synthesis, transition metal catalyst and organ catalyst, domino reaction, and multi-component reactions. So his talk is basically chemical synthesis of recent advancement. And this is the as this nanotechnology, the FDP program is multidisciplinary and interdisciplinary. So this talk, his talk will enhance the basic ground of the catalyst preparation, how the synthesis reaction, and that more on that. So I invite Dr. Chandicharan Malakar for his talk entitled "The Application of a Release and a Catch Catalyst." So welcome to Malakar, Dr. Malakar. Please share your PPT and start your talk. Thank you very much.
So thank you, Professor Bihu, for your so elaborative introduction. Um, and I'm indeed glad. Am I audible?
Yes, yes, please.
Uh, I'm indeed glad for giving me this opportunity to be a part of this program. And today I'll be talking about, as Professor Bihu mentioned, the application of release and catch catalysis. So before we go, I feel since several participants are from interdisciplinary background, just to refresh our previous concept, we would like to see what is catalysis basically. So the catalysis is the process of increasing the rate of the chemical reaction by adding a substance known as catalyst. And we know which does not consume in the reaction, and after the finishing of the reaction that could be recovered. And if we see the two types of reaction, this is a non-catalytic, that means in absence of the catalyst, and this is the activation energy in presence of the catalyst. That means in presence of the catalyst, the activation energy barrier goes down, and this is why the reaction goes faster in an effective manner. So what should be the outcome with the catalysis, or why people do catalysis basically, not the conventional reaction? For higher selectivities and obviously for higher activities of the substrates for the reaction, the improved raw material and energy usage, minimization of waste. So through catalysis, maybe the reaction can be diverted to the specific path. So that's why the minimization of waste can be done. So the catalysis is also important because in worldwide, a huge amount of revenue can be generated using the catalytical process. So you can see here the uh, catalysis in which field it is applicable, like in chemical, in refinery, in polymer, and environmental. Approx 9 billion USD is worldwide revenue generation happens. So we learned a nice term that catalysis, and we all know how it works and why it works. But what is the challenges basically? The current industrial processes. Here I have shown not only for pharmaceutical, but not only pharmaceutical, rather chemical, any APIs, refineries, polymer, and all these things. What actually the problem faced by the industrial processes. First of all is poor scientific productivity, and another one is manufacturing cost. So why the manufacturing cost is actually the problem? Because most of the processes use homogeneous catalysis. Yeah, some processes use heterogeneous catalysis which are well developed, but not all the processes. So that is the biggest problem basically. So if the homogeneous catalysis is used, uh, then the catalyst cannot be recovered. Okay, and finally that becomes waste, and whatever the amount we use. And poor scientific productivity means, yeah, so many processes does not go well because of the catalyst activity, because homogeneous catalysis has some uniform catalytic activity overall the catalytic process. So that's what, this is a biggest concern for industry, to have the modern concept in the catalytical process or catalyst design. So we know homogeneous catalysis, I have already talked, and we all know that everything, your substrate, product, and catalyst, these are in the solution, in one solution, and your product is also in one solution. From there, if after the chemical process the product has to be purified, that means we need to purify from the catalyst, your substrate, byproduct, and all this mixture. Out of all this mixture, we need to separate it out by some purification process. We'll come slowly through other processes. And how heterogeneous catalysis? Your substrate comes in contact of your any support material, and that adsorb on the surface of your supported catalyst or catalytic material, and the adsorption can be by physisorption or chemisorption. So we know all these things, and then the product forms. And finally, the catalyst we can actually get by simply filtration process. So yeah, homogeneous catalysis, heterogeneous catalysis, we know the in heterogeneous catalysis actually very low atomic efficiency, but in homogeneous catalysis very high atomic efficiency. And most problem is the poor stability of homogeneous catalysis and hard to recovery. But in this, the heterogeneous catalysis, that is the reverse. This has a lot of advantages in this sense. So what should be the ideal chemical synthesis? If we talk about catalysis, it should produce minimum of waste, use available feedstock, apply energy efficient process that should be 100% atom economy, which could not be done using your homogeneous catalysis. High selectivity and perform reaction in standard equipment. Okay. So apart from all the other problems, as we mentioned, that recovery of catalyst or recycling of catalyst, this is the biggest concern in today's uh, industry and chemical processes. So homogeneous catalysis, in this sense, it facilitates a high degree of tunability of the catalyst activity and selectivity. However, the need for additional separation such as distillation, extraction, and chromatographic method required to remove the homogeneous catalyst from the product mixture, coupled with the lack of efficient recycling methods, may restrict their use. Although these are very much useful for the synthesis of fine chemicals. So further drawbacks, what we can understand, the homogeneous catalyses are very high in price and leaching of the metal ions, which cause the problem in terms of laborious removal of the metal ions from the mixture. And quite often it requires also high catalyst loading, like 10 to 20 mole percent, even more. But on the other hand, what happens with heterogeneous supports? This allow efficient recycling by filtration. The ideal heterogeneous catalytic system will maintain the catalytic efficiency of the homogeneous counterpart and will indefinitely be recovered and reused with any loss of activities. So that somewhat we know, but the possible regeneration of the catalytic system could restore the original catalytic activity in case of heterogeneous catalysis. Okay, several methodologies have been devised basically. Um, what could be the first in case of heterogeneous catalysis? The first one, the first active catalyst can be covalently linked to some kind of support. So the catalyst, the active catalyst can be covalently linked with some kind of support, and such support can be soluble or insoluble. Okay, if it is insoluble support, then after the reaction it is very easy to separate, because just only via filtration. But whereas if you have the soluble support, then there is a big problem, because after completing the reaction, the precipitation method has to be occurred. Then only we can recover the support. The second type of recycling method is the biphasic catalysis. So the biphasic catalysis is what? The selective partitioning of the catalyst from reactant and product. That can be achieved by employing two immiscible solvents in the separation step. That also can be done, and which materials are generally used, like aqueous phase catalysis, fluorous biphasic catalysis, supported ionic liquids, and supercritical fluids. The third one for recycling process for the heterogeneous catalysis would be non-covalently supported catalyst. And in this case, the catalyst can be adsorbed, dissolved, or included or linked by electrostatic interactions in several support. So these are the generally known or traditional method used. So the recent improvement, so that should refer to the release and catch catalytic system, and that is also known as boomerang catalytic system. What is boomerang catalytic system then? This system is prepared by non-covalent immobilization of the catalytic moiety on proper support. So if you take the support and you just immobilize the catalyst on the support, and then this becomes the heterogeneous system. But this heterogeneous system in the reaction, it cleaves the support from this designed support and catalytic material, because you have the substrate inside, because the substrate need the catalyst. Once it cleaves the support from the catalyst does the reaction with the substrate and give the product, and after completing the reaction, once again the support capture the catalyst. This is why it's called boomerang or release and catch catalysis. There are several materials which has been actually explored or described in this regard. So one example is like catalytic system which use the carbon nanotubes and pyrene tagged with pyrene. So we know pyrene, the carbon nanotubes are very interesting material because of their mechanical and electronic or chemical stability. Some example of them are reported on their use as a support for covalently linked catalysis. On the other hand, we can also understand the carbon nanotubes can also be employed as a support for non-covalently linked catalyst, which can be released and recaptured during the reaction. To do so, what happens? You have the carbon nanotubes and you have the pyrene, the highly pi electron rich pyrene material, and then this is non-covalently, this is actually covalent, non-covalently linked with the carbon nanotubes by pi stacking. And what happens here? If you look carefully, the solvent play the role and temperature in a specific temperature. This non-covalently bond can be sometimes released, or in some temperature it can be restored. Once the pyrene get detached from the carbon nanotubes, so which is actually bonded to the catalytic materials, and then it comes in the contact of reagent which complete the desired chemical transformation and give your product. So this is one. In this case, what happens? The pyrene, rhodium, and some phosphorus materials has been tagged with carbon nanotubes, and which gives the desired your hydrogenation reaction. So this can be actually adsorbed on CNTs by ethyl acetate. By ethyl acetate, this can be adsorbed on CNTs, and then it could be detached by dichloromethane. So the 10 cycles has been performed. 10 times it has been the catalyst has been recovered, until ninth cycle the catalytic activity was restored. But in 10th cycle also the catalytic activity and other selectivities has been restored, but the drop in the catalyst, I mean the activity of the catalyst has been observed, the dramatic drop basically. You can see other example like carbon nanotubes, then the pyrene which is embedded with the ruthenium metal has been tagged, and with this material the reaction has been done 6 times. 6, or you can tell this is up to 8 cycles is it has been done for 6 times. So with good selectivity of the product formation, and the conversion. So if we look at another material like a pyrene tagged N heterocyclic carbene complex, this N heterocyclic carbene complex was immobilized on the highly magnetic graphene coated nanoparticle through pi-pi stacking. The palladium complex was used in the hydroxy carbonylation reaction. That means you take aryl halides and then under carbon monoxide atmosphere, the corresponding carboxylic acid has been formed, which is a very valuable material for the industrial purpose. This complex is dissociated from the nanoparticles during the course of the reaction in water at 100 degrees centigrade. So this has been dissociated at 100 degrees centigrade and was recaptured on the graphene layer at room temperature. And when we once again cool down the reaction mixture, this goes back. So in total, 16 cycles were carried out, and after each cycle, the catalytic material was recovered by magnetic decantation. The catalyst loading was 0.1 millimole per gram, and which was actually followed by ICP AES spectroscopy. 63% of the palladium complex was dissolved from this complex 5 after filtration on boiling water. So at 100 degrees centigrade, that actually gives the 63% of the palladium complex for the catalyst in the reaction. So another similar type of material, we can also see that the carbon nanotubes and the pyrene, which is embedded with gold nanoparticle, a gold complex. And then with this, the conversion of 100% has been achieved from 1 to 4 cycles. But this gives the drastic reduce in the conversion at the 6th cycle. So this has been also recaptured by lowering the temperature. If you increase the temperature at around 30-40 degrees centigrade, the reaction will happen, and cool down the temperature, it will go to and then in situ some heterocycles has been formed and which can be tagged with the carbon nanotubes by pi-pi stacking. Palladium nitrate has been adsorbed by electrostatic interaction, and then the reaction can be done, which gives them palladium nanoparticle immobilized carbon nanotubes, which has been used for a very valuable reaction. This is kind of carbon-carbon bond formation, Heck coupling reaction. So the palladium concentration in the solution has been correlated clearly here. One can see with the progress of the reaction. This clearly says that the dissolved molecular palladium represents the true catalytically active species, and the prepared palladium and metal oxide solids are simply precursor of the true catalyst. So it has been compared with some other materials also, in which we can see the palladium is deposited back onto the support at the end of the reaction, and this phenomenon we can understand as release and capture or dissolution or deposition of mechanism. So till fifth run, it has been also compared with some other catalyst like palladium oxide single walled carbon nanotubes, palladium oxide multiple wall carbon nanotubes, and palladium oxide carbon nanofiber, palladium oxide graphene oxide, and palladium oxide reduced graphene oxide. These five are already compared. So which shows the palladium oxide and reduced no, palladium oxide graphene oxide shows the turnover frequency 4144 with yield of the product 80%. So that shows the better efficiency basically. So if we look at some other material, similar type of material, but it's little bit in a different way has been represented. These are actually silica material, catch and release catalysis by carbon nanotubes, which is embedded with Fe3O4 and silica and palladium catalysis. The palladium nanoparticle on an amino vinyl silica functionalized magnetic carbon nanotubes has been represented here. One can see their core shell is carbon nanotubes, Fe3O4, silica and palladium, which is functionalized with the help of stability of the palladium nanoparticle, and is responsible for the reduction of palladium 2 to palladium 0 without the need of adding any external reducing agent. And this catalyst can be used successfully for the Heck reaction. And similarly here, the pyridine derivative, which is also coordinated to palladium and immobilized on magnetic nanoparticle, can be also used. And here one can see the silica coated your Fe3O4, which is embedded with the ionic liquid type of materials that bonded with the palladium, can be also used for this use as a catalyst. So as we just mentioned in the previous slide, the ionic liquids can also be used as the recycling system as biphasic catalysis. So this is one example of ionic liquid based release and catch catalytic system, which is based on ionic liquid. So what is the major, the major actually limitation in the traditional biphasic ionic liquid organic system is the need of relatively large amounts of ionic liquid, which are still expensive basically. In addition, the high viscosity of the ionic liquids compared to the classical organic solvent can induce mass transfer. Both these drawbacks can be circumvented by immobilizing thin film of ionic liquid onto high surface support. So yeah, this is actually, this can be done by the supported ionic liquid phase approach, which involve the presence of support material. You have the presence of support material, and that is modified with the absorbed layer of ionic liquid serving as the reaction phase in which homogeneous catalyst is confined. So your homogeneous catalyst is confined here, and your support material is here, and this is actually bonded through the linker and the ionic liquid. Now this how this works basically. So if we have the solvent, if we give the solvent that the linkers between the catalyst and the ionic liquid which is supported, which is embedded to the support material, will cleave, and the catalyst will become free. The catalyst will become free, and that will do the job for the desired chemical transformation. And when we remove solvent, this whole system once again will combine, and it will retain as it was. So this concept was also actually employed in asymmetric catalysis. So one of the example we can see here, the catalyst. Here the proline has been embedded as the catalyst as the catalytic material, and the ionic liquid, which is this is trifluoroacetate moiety as an anion has been embedded. And if this material has been given in water, then actually this bond will be cleaved and your catalytic moiety will come out, and that will do the job. So with this material, 15 cycles was achieved with high conversion and very selective, and in a very selective manner. So we have seen some pyrene tagged carbon nanotubes as a release and catch catalytic system. We have seen some ionic liquids, and there are some other concept for the release and catch catalysis, that is actually reverse flow adsorption. So the reverse flow adsorption also can be employed for the release and catch catalysis. And when a non-covalently supported catalyst is employed, it is believed that only batch conditions or batch reactions can be used. But this is not true. The release and catch catalytic system can also be coupled with the flow system. This is basically in a flow system can be done. An interesting concept for the recovery and recycling of homogeneous catalysis is based on reverse flow absorption, which combines adsorptive separation with the reverse flow technology. It is essential that the adsorption is reversible. The adsorption has to be reversible, otherwise this process will not work. And it should also reintroduce the catalyst into the reactor with the reactor feed. You can see here the reverse flow adsorption. The substrate is pumped into the reactor through the path A and dissolve the catalyst from catalyst bed 1 until the bed 2 is saturated. Until the bed 2 is saturated. Then the flow is reversed and substrate is pumped through the route B. And finally, the product can be purified. So the example of this catalyst, you see the pyrene tag, the ionic liquid based palladium catalyst is there. And yeah, this two catalyst, one is bonded with phosphine, and in another cases, the both side is palladium. In other case, both side is palladium. So this has been employed for the Suzuki type of reaction. So this is release column. The reaction occurs and the catalyst capture column, and finally we got the product. With catalyst 10, 86% conversion has been done, and it has been seen that 5.1 millimole leaching after 15 minutes. And with catalyst 11, 99% conversion can be achieved and 0 millimole leaching after even 30 minutes. That means the phosphine is not that much durable under this reverse flow adsorption. So if we see the reverse direction, 64% conversion with 10 with 4.4 millimole leaching in 15 minutes, and with catalyst 11, 99% conversion can be achieved and only 6.4 millimole leaching after 30 minutes. So yeah, this is a good process nowadays, applying applying as flow process in the industrial method. So this reverse flow approach also can be based on other substrate support interaction. So the support adsorbent can be functionalized with the well-defined binding motif and the complementary motif covalently attached to the ligand, that is substrate. And this supramolecular anchor enable one-step simultaneous adsorption of the catalyst, that is metal ligand complex, and excess ligand onto the adsorbent material. This non-covalent supramolecular host-guest anchoring strategy for the immobilization of homogeneous catalyst was also investigated several times basically, and this is actually sufficiently allows the strong catalyst immobilization and efficient catalyst recycling. So based on this strategy, one can see that the porous silica material has been embedded with the linker like
From
carbon
second router,
and
we actually added the network for fast router, but third and fourth router we did not add it, so we need to add them. So it will be 3.0, and the mask will be class 3, class C IP address. So
somebody talking. And then your rhodium and the proline type of ligand, that is not exactly proline, but this your pyrrolidine type of ligand can be taken, and the silica supported porous materials can be synthesized, and which has been employed for the asymmetric hydrogenation. So release and catch catalysis approach by palladium catalyst immobilized onto supported ionic liquid like phases. So that is we tell as SILLPS. And if it is gel, then it will be gel supported ionic liquid like phases. So this is also amongst the others studied material for the reversible immobilization of the palladium and applied in many chemical transformation for carbon-carbon bond formation. And for this purpose, actually, ionic liquid like ligands which has been anchored to the gel type polystyrene resin and the palladium 2 precatalyst. The palladium 2 precatalyst bound as N-heterocyclic complex. This support is very well demonstrated to release and stabilize and recapture the formed palladium nanoparticles, preventing the formation of less active palladium black for 5 cycles. And this is used generally for Suzuki reaction. And the similar type of material, ionic, liquid based and porous silica has been also shown here. This shows almost similar catalytic activities. Yeah, this methodology also has been employed using the palladium, which is also directly coordinated to the phosphine ligands. And one more materials also has been shown, that is based on the gold nanoparticle. This has been bonded through actually the sulfur atom, the thiol functional group, and this palladium is bonded here to the ionic liquids, and which has shown the maximum activities and recycling and recapturing abilities as a catalyst. One more interesting materials can be shown here, that is actually C60 tempo 10 catalytic system, like to be microspherical gold support through a covalent sulfur and your gold bond. This C60 material, C60 tempo actually 10 on gold composite or palladium catalyst had a particle size of 0.5 to 0.8 micrometer and was covered with the fullerene derivative of 2 point is fullerene derivative of 2.3 nanometer diameter, bearing 10 nitrosyl group, the 10 nitrosyl groups. The organic film sold up, this is sold up to your 10 nanometer thickness. The catalytic composite allowed for the oxidation under mild condition, under various for the various actually primary and secondary alcohols to the corresponding ketone materials. And this is actually giving the typical homogeneous catalytic, and while retaining the same time the advantages of all heterogeneous catalytic the heterogeneous properties of the catalytic system, and which can be easily separated from the reaction mixture. So the materials has been actually characterized. As we know, ESR repair is actually very challenging task for the uh, to analyze. This is which is due to the presence of many different transition from different spin states arising from the multiple interaction between numerous radical units, and the diversified exchange coupling mechanism, including like electron spin exchange mediation through the bond or through space. In this case, for the fluorine case, the C60 tempo 10 or polynitroxide, the EPR spectrum gave direct spectral evidence for the presence of two contribution expressed by 3-line signal, plus a contribution from a broad component on raising the temperature up to 160 calorie, 60 Kelvin. And the relative intensity of the 3 lines diminished with the temperature. One can see with the temperature is diminished, which may have been a result of an increase in the strong spin exchange between the NO group present here. This has been also characterized by CV, the using cyclic voltammetry. So CV obtained for the solution of tempo functionalized fullerene, that is C60 tempo 10, and this is actually thioacetate. If you see, this is a one thioacetate bond functional group is there. The close to reversible system of the redox peak at 0.8 volt is attributed due to the tempo and tempo plus redox couple that can be understood, which confirming the presence of nitroxyl radicals on the surface of synthesized C60 fullerene derivative. As expected for its hexakis adduct, this is a hexakis adduct of the fullerene derivative. One main reduction signal is present in the corresponding CV curve, and this signal is notable shifted towards the negative potential comparing to the value of the registered for pristine C60 fullerene derivative, allowing us to conclude that this material has significant lowering electron accepting properties, and when compared to the unfold C60 materials, this is the unfold C60 material, core. And the additional small peak would be probably be attributed to the traces of fluorine derivatives, which is lower functional group, in this. So we have shown a lot of things regarding the pyrene derivative. So one more interesting example using pyrene, we can see that this is an active and recyclable supported catalyst that involve actually molecular. So let me show the next slide first. This blue ball means this is a terpyridine is there, which is coordinated to the ruthenium. So which actually involves a as a active molecular ruthenium terpyridine complex, and their ability to promote the transfer hydrogenation of nitroarenes in propanol. So what is actually done here? Your pyrene is tagged with one terpyridine, and here actually 5 terpyridine is tagged with one pyrene. So, and which has been actually immobilized on the magnetic nanoparticle, and then we can see here this complete assembly. If we increase the temperature of 8 till 80 degrees centigrade, this can be dissociated from the support, and which can involve in the reaction in presence of ruthenium catalyst. But if we decrease the temperature till 20 degrees centigrade, and which can be recaptured, and this pi stacking will be dissociated and recaptured with the temperature variation. And once it is dissociated, the free ruthenium in the solution can capture this either mono terpyridine tagged pyrene or 5 terpyridine tagged pyrene, and give the reducing reaction of nitroarenes. So one can see the morphology study. So the before a catalytic cycle and after 5 catalytic cycle, this is actually the monoterpyridine tag ligand. After 5 catalytic cycle, morphology has been bit disturbed, so which shows the catalytic activity may have been little bit diminished. So we have also contributed in this religion catch catalysis. So one of the aim we had is actually in the industry for the pharmaceutical for the active pharmaceutical ingredient synthesis, the amination reaction is, or rather asymmetric amination reaction has been tremendously used, and which is a very valuable reaction for the industry. So for that, actually very large amount of catalyst loading is required. That is actually maybe 1 to 2 mole % or sometimes even more. This is why the industrial application sometimes hampers. What we tried to design is, we have taken the iridium catalyst, which is embedded with the phosphoramidite ligand, and then we try to immobilize on the silica supported material, and then we can via electrostatic interaction we can get the supported iridium catalyst, which has been employed for the amination reaction. So this is suppose your amine group, and we observed that if we immobilize 0.42 mole% iridium, which is in comparison to your 1 to 2 mole%, it is very low. We can do the amination reaction up to 11 cycles. 11 times we can recover the catalyst, and we can show the catalyst activity till 8th run. Till 8th run we have shown. So in the first run it is the reaction is very fast, and in 8th run the reaction is not that slow, because in traditional condition in traditional condition, although if you have if you use the same catalyst load, the reaction takes more than 2000 minutes, but here in 8th run we can do the reaction even less than 200 minutes. And in conversion in each, or even conversion, yield, your selectivity of the product is almost similar in till 8 cycles. So to improve this, actually we have tried to immobilize 0.9 mole% of the catalyst instead of, here we have shown here 0.4 mole%, but we have now immobilize in this case 0.9% of the catalyst or iridium on the support. And then we have seen under the similar condition we can recycle the catalyst till 34 times. Here till 33 times it is shown. We can recycle the catalyst till 34 times. And from the first cycle to last cycle, we studied the leaching of the catalyst because in the catalyst we have phosphorus. The phosphorus NMR has been done from the solution of the reaction, and we can see till your 8 cycle, till your 30 cycles, the catalytic is restored in the restored in the support in a larger amount, but it drastically dropped in 34th cycle. But the reaction was performed in tetrahydrofuran. But when we changed actually the solvent as toluene, the reaction can be conducted till 43 times. The reaction can be conducted successfully till 43 times. And in all the cases, although you can see in the 43 times, the yield is decreased, but selectivity almost retain, but yield is relatively decreased. So that means the amount of catalyst on the support does not differ the selectivity of the product or in the formation of the product, but it actually little bit disturb in the yield of the reaction of the product. Here also the leaching has been studied, and we can see here from the beginning the catalyst amount in every I think 8th interval we have performed, and in 43 cycles in 43 cycles the catalyst is still retained in a larger amount, although it is not much in compared to the beginning, but it is wonder that it still retained on the support of the catalyst. So in last, actually, I just want to shortly mention the release and catch catalysis is also studied or investigated by the cavity-driven aggregation of the nanoparticle. So although I'll be not talking much on that, but what happens actually, this is a concept based, and now in the recent times this becomes a huge research area. We take a material which is, you can see, we can design a material. Now in this, inside the materials, we assume that by single crystal analysis we can find the space also, what is the space available in the cavity of this molecule. Now if we encapsulate the palladium and some other reagent inside the cavity, now the palladium nanoparticle should form, but the palladium nanoparticle cannot form in its own way. Rather, it should be driven by the cavity formed inside this molecule, or the space allowed inside this molecule. It cannot go beyond that space. And then which nanoparticle forms, in that we can encapsulate some reagents and substrate, and that will give the specific product formation, which does not actually allow under the traditional reaction conditions. So if under the traditional reaction condition, suppose the product A forms, but inside the cavity of this material, it can give the product B. So I think I should conclude here, and finally I should acknowledge AICT and ATAL for this for the funding for this event, and NIT Manipur for the support, and Director NIT Manipur for allowing us to be a part of this, and Professor Vibhu Prasad for inviting me to give a talk. Thank you.
Thank you, Professor Malakar, for your interesting and informative talk. Now this is the time for these participants' questions. So if any questions or query, or even if a very small suggestion, then you can ask question to Dr. Malakar. So please. Any questions? I think there is no more questions. So I conclude and rest the talk. I thank to once again. I thank to Professor Malakar for his talk, and we should wait for the next talk. That is 12:15 by Professor Ramesh Mallik,
Thank
Associate
you very
Professor,
much.
Department of Physics, IIC Bangalore. So we should wait for them, wait for him for his talk, and his talk is a tetrahedral as a thermoelectric material. It is one of the most interesting topic. So please, it is the means we can tiffin time. So and now it is going to be lunch time now. Okay, thank you very much for this thing.
Hello. Hello.
Good afternoon, everyone.
Good afternoon.
Good afternoon, sir. So this is our fourth day and second session of faculty development program. And today our speaker is Professor Ramesh Malik, Associate Professor, Department of Physics. So before I should go for the inviting him in for a talk. I should introduce him. Professor Ramesh Chandra Malik obtained his master degree in physics from Berhampur University, Odisha, India in 1998 and a PhD in physics from Indian Institute of Technology, Madras, Chennai in 2005. He is currently an associate professor in Department of Physics at Indian Institute of Science, Bangalore, India, working in the field of experimental and condensed matter physics, specialized in bulk and thin films of thermoelectric materials, devices, sensor, and prior to IIC Bangalore, he was working as a Marie Curie postdoctoral research fellow at German Aerospace Center, DLR, Cologne, Germany, with Professor Ikahard Muller as a postdoctoral research fellow in Korean National University of Transportation, South Korea, with Professor Il Ho Kim. His current research is on the charge and heat transport on the semiconductor-based device and a nanoscale energy conversion device with focuses for thermoelectric. He has many achievements. He has received in many projects. He has published more than 100 international journal paper. So I invite Professor Malik for his talk. Tetrahedride as thermoelectric materials. So we welcome Professor Malik for the FDP program, and I request him to deliver his talk and some of knowledge he will distribute to us. Thank you very much, and over to Professor Malik for his talk. Thank you.
Yeah, so good afternoon, everybody. Thank you very much, Professor Bibu Prasad Swine, for your nice, kind introduction. So, uh, it is really wonderful, though personally we don't meet each other. So, sitting at a different part of India, also we can deliver the talk and which with solve the purpose. So, let me share my slide. So, is it visible?
Yes, please. Yes, please.
Yeah. So, okay. So today I will talk about tetrahedride as a thermoelectric material, and this is one of the topic I'm working last several years, and I hope the information I have kept as a very simple way so that it will be interesting for you, and maybe I will reach to almost all the audience. And nevertheless, if you find difficulty, please stop me and ask the question. So because we don't see each other, and I don't know how far you will be able to get the things, but nevertheless, wherever you find difficulty, please stop me and ask the question. So basically, I will just introduce to this thermoelectrics, introduce to this tetrahedrite, and how to enhance this thermoelectric property in tetrahedrite. How, whether this is the same conventional way we will go for it, or there is some divert route that we have to see, and some of this motivation that why we choose this tetrahedride and what is this transition metal substitution in a tetrahedride. And after the this and the next part, I will take you to the this was a single element substitution, and I will show you that how double element substitution also help in the tetrahedride to improve the thermoelectric property. At the end, I will conclude it. So, yeah, so last year was the year of 200 years discovery of Seebeck effect. And many people say that, okay, the efficiency is so low, why this research and all those things. So how far it is, this is
Sir, sir, your voice is breaking. Please little louder and please.
yeah,
It
yeah.
will be good.
Okay, so is it fine now?
Yes, please.
Yeah, okay. So now, so when this low efficiency things it is coming to the picture, now let us look at it. See, you don't really need all the times a very high energy or high power output all the times. So there are a different field or different place. You need a different range of power. That requirement is there, starting from 1 microwatt to some several kilowatt power is required and different stage. So suppose you want to make a sensor to be work. For that you need only few microwatt, not kilowatt. Or in a large scale heat recovery transport vehicle, there you need some kilowatt. So even the thermoelectric having the low efficiency, but it is a very handy technology that can help you in apply in a very difficult place where no other alternate solution is there. So that's why this is one of the important field. And now you can see that. So the beauty of this technology is that when you give a input to something and your output is something like 30%, 34% is used as a useful way, and so if you want to use the thermoelectric as a generator or as a tapping device for the power generator, so you don't have to really go for putting some effort to give a input. There are plenty of waste heat available everywhere, starting from your body heat to wherever you look at, everywhere you can see the waste heat. And that waste heat can be tapped into the useful way to harvest the energy. There are many interesting applications. This is part is radioisotope thermoelectric generator. To this is from the BMW car they have integrated, and this is the space mission. So everywhere this thermoelectric device can work. So how this technology working? This is working in a very simple the simple principle. It is called Seebeck effect. The Seebeck effect is nothing but when two dissimilar junctions held at a two different temperature, so there will be a potential generated. And if you can tap this potential, then that will be your useful way of energy harvesting. And the reverse of it, so when you pass the current between two dissimilar material junction, one end will be getting cool and the other end will get heated up. So that is the way you can make it as a thermoelectric cooler. So this is the way it works. And combining both the effect in a single conductor when you are unequally heating it and passing through the current. So one end of the heat will be absorbed and another end it will be absorbed based on the direction of the current. So that is Thomson effect, and this correlates the both Seebeck effect and the Peltier effect. Nevertheless, this is the basic principle. But you talk about now this device. So how the device is working? When we talk about the device, we talk about the efficiency. Efficiency means the output power divided by the input uh, uh, input value, whatever you are giving. So here it is a game of only heat. So you give a waste heat, how much the power you generate, that is what the this parameter give you efficiency. So efficiency is nothing but the first term is Carnot efficiency term times the thermoelectric efficiency. And here one parameter is there, it is called Z times T. So Z times T is nothing but it is a thermoelectric figure of merit. So which is, this is again a thermoelectric figure of merit of a couple. So that means when two materials, P type and N type, they are connected in a electrical series and thermal in parallel, so they will have both product of the Seebeck coefficient, thermal conductivity, and electrical resistivity. So this is the way it is defined as the figure of merit of a device or a couple. So N stands for N-type material and P stands for P-type material. And if you want to see a single element, the figure of merit, which is nothing but S square sigma by Ke plus Kl. So total thermal conductivity is composed of lattice part of the thermal conductivity and the electronic part of the thermal conductivity. And the interesting part is, if you really look at it, this S is your Seebeck coefficient, which I defined previously. So this Seebeck coefficient is related to the carrier concentration, which is inverse of the power 2 by 3. So that means if the carrier concentration increase, the Seebeck coefficient decrease. But the thermal conductivity has the electronic part, which is directly related to the carrier concentration. And electrical conductivity, you can see that it is also directly related to carrier concentration. So when you look at this plot gives you very nice idea about carrier concentration versus Z times T. So, and different parameter is plotted here. So the left side is, it is a low carrier concentration or insulating one, and the right side is a high carrier concentration, it is a metal. In between it is a semiconductor. So the different parameter, as I explained, that is varying based on that. And when you look at S square sigma, it is called power factor. So this is the product of or Seebeck coefficient square times the electrical resistivity. So that is coming high at in this range. So that means in a semiconductor range. So, and if you look at the Z times T, so that is also coming in this semiconductor range. So then you have to look at the material which will have this carrier concentration in a degenerate semiconductor range. So, and this Z times T, that is related to the efficiency. Already I have shown you this formula. So now you can see that this plot, it is a beautiful plot where this is the temperature versus efficiency with a delta T. Top is written as a delta T. How much the temperature difference you work with, what delta ZT, and how much efficiency you can get. So this is the line for ZT 1.6. When 1.6 ZT is there, you can get an efficiency of 10 to 11% at working between the temperature of 300 Kelvin to 500 Kelvin, maintaining the delta T at 200 Kelvin. So similarly, if you go higher and higher, so you can get a 15% efficiency with the same ZT at when delta T increase to 300 Kelvin. Or you can look at also lower ZT with a higher delta T also, that can be also possible. So this gives a fair idea that why people are worried about the thermoelectric material improving ZT. ZT improve means your efficiency improve. So that is what it is. So now this is not basic idea. Now let us look at that, how we will look at the material aspects. Which material will be suitable for this thermoelectric research, or every material is any semiconducting material will be suitable. No, there are certain finger rules that you have to look at it before starting your research. So you should first look at the crystal structure of a material. So if the material will have a highly crystal symmetric crystal structure, then it will give you the high band degeneracy and high power factor. So you remember that one term I used previously, power factor. So you want to get a high power factor, you should have a highly symmetric crystal structure. It should be a heavily doped or degenerate semiconductor. Already I have shown you that a graph that how why people are worried or really interested in the semiconductor range, because at that range the power factor is high and ZT also touch to high. So that's why you have to look at the degenerate semiconductor which carrier concentration in this range. And you need also light mass compound with a low thermal total thermal conductivity, that is related to the D by temperature or frequency is related in this way. So you have to look at it, and that is what you always you don't find in every material. One of the interesting material is tetrahedrite. That's what today I will talk. And other aspects you have to look at complex crystal structure. That means the crystal structure should have many atoms per unit cell. That means low fraction of acoustic mode and low lattice thermal conductivity. So your thermal conductivity will be low. That is what it is required. And the large effective mass of the charge carrier, which is related to the Seebeck coefficient in this way. So it is here, it is the effective mass, it should be large. And the high carrier mobility, which will give you a better electrical conductivity. And you have to look at the narrow band gap, or it is a reasonable good band gap, something like 10 kBT or a little above. So if you have a very low band gap, then the bipolar effect will come. If you will have a very high band gap, then it will go to insulating one and it will compromise with the electrical conductivity. So tetrahedrite satisfy almost all the above points. So that's why we are interested for this tetrahedrite as a thermoelectric material. So now you look at this high crystals, high symmetric crystal system, that is a cubic in the this also this will leads to a electronic band maxima and it leads to improve the power factor. And this has a complex crystal structure with large number of atoms in a unit cell. Probably that will scatter the phonon and you will have a low lattice thermal conductivity. So this is quite interesting fact about the thermoelectric and satisfy almost all these sort of things. And apart from this, you can look at the way the different approaches that can enhance the thermoelectric property. So one part is power factor, that is S square sigma, and another thing is the thermal conductivity. So to improve the power factor, you can optimize by charge carrier concentration, by doping or substitution. You can introduce a resonance or impurity state near the Fermi level by doping substitution, increase the band degeneracy, increase the effective mass in a different approach to improve the power factor, and to reduce the lattice pattern for total thermal conductivity. You can create an anharmonicity by doping or substitution, reduce the uh, electronic part of the thermal conductivity by doping or substitution, various synthesis route by doing this grain boundary scattering or phonon scattering nanomaterial. So many approaches you can improve this. So let me clear here that The present material, whatever we are going to discuss, the tetrahedrite does not fall in a conventional thermoelectric material. Where conventional thermoelectric material people dope or substitute to improve the power factor by increasing the carrier concentration or increasing the electrical conductivity, all these things. But this material has intrinsically very high electrical conductivity and low low thermal conductivity. So you have a very limited way to improve the Seebeck coefficient, which is a unique problem, not a conventional thermoelectric way. It does not go. Now look at all this property, whatever we discussed, that these are different state-of-art thermoelectric materials, starting from bismuth antimony, which is a low temperature material. Lead telluride is room temperature. Bismuth telluride room temperature. Lead telluride above room temperature. And scutride and tetrahedrite. This is a little bit high temperature material. So whatever the things I was telling, you can look at it. This is a very high crystal structure, is highly symmetric, and this has a very large number of atoms per unit cell. That's what the initial slide I was telling, that you should look at it. It has a very high, large number of atoms per unit cell, which will give you a band degeneracy and reduce the thermal conductivity. And electronegativity difference between them is very low, and it will form a covalent bonding. So almost everything is good for the tetrahedrite. So now let me introduce the tetrahedrite. Means it is a structure. I repeated it one, but this is a particular mineral or material form that a tetrahedral structure, which is copper, antimony, and sulfur. Copper 12, antimony 4, sulfur 13. So this form the tetrahedrite structure, and this is quite a unique material that we will know. And this is the timeline for selected thermoelectric material, starting from, you can see that from 1950 lead telluride to it marched for the high jetting. So even 2013 this tetrahedrite came, then all this SNAC and many other material has been discovered and that has been reported. So why is this tetrahedrite is so special? Let us look at it. So this material is available as a natural mineral in mineral form. So you don't have to really work much hard to prepare in the laboratory. Even whatever I am going to talk about, it is a synthetic tetrahedrite that is prepared in the laboratory. But in mineral ore form, this material is available in the nature, and this is a environmental friendly material. Whatever the material I discuss about lead telluride and other material, they are toxic. They are toxic, and it is also very high cost. But this is a cheap material, environmental friendly, in form of minerals available. And Karnataka has also in Kolar has also this mineral. It is available as a geological survey. It says so. India also we have. So the general formula stands for like M1, M2, M3, and S13. So M1 stands for copper or silver, M2 is manganese, iron, cobalt, nickel, copper, zinc, and and so the charge balance between them is M10 plus 1. So this is the oxidation state for first M1. Then M2 oxidation state 2, and M3, which is M4, the oxidation plus 3, and S13 is a oxidation state minus 4. This is very, very important, and if you look at the, they have the charge balance and it is a neutral. And already I have discussed that this has a complex crystal structure. This has a 58 atom per unit cell, and moderate Seebeck coefficient, high band degeneracy, And look, already it is reported that the jet is something like close to 0.7 or 0.1 with a different approach. Now, this slide, bit careful and you have to look at it. So it is a natural occurring p-type mineral with a nominal formula. Composition is copper 12, antimony 4 and S13, and it is a non-toxic, earth abundant and environmental friendly element. And this has a body-centered cubic structure which has a, the space group is given by here. But look at this. This is a very important information for the talk. So copper has a two Wyckoff position, 12D and 12E. And 12D position, it contains both oxidation state, copper +1 and +2. In copper 2 position, oxidation state is 1. Sulfur has also two Wyckoff position, 24G and 2A. And 24G, it has a -2 oxidation, 2A position also -2. And antimony has 8C, which is having the oxidation state +3. So which is that previous M1, M2, M3, S13, that is what it is related to this. And if you look at it here, copper +6, TR means triangular, it is related, and tetragonal, sorry, so pyramidal. So like this it is there. So this is the crystal structure, and they are bound in this way. Now, the beauty of this metal is you can see that the antimony and the sulfur is related in this SBS3, that is a trigonal pyramid way, and the other one is also SBS3, that is trigonal pyramid way. But the other part which is related copper with sulfur, I told sulfur has two Wyckoff position, so 24G and 2A position. So this copper is bound with one sulfur here and other sulfur here. And when the copper vibrates, this brings the anisotropic property inside this material. Because of this, the material is intrinsically low thermal conductivity. Now you look at, this is the pristine tetrahedrite, which different groups, they have published different results, and you could see that it has a very low electrical resistivity. This is all pristine sample. And Seebeck coefficient is a moderate Seebeck coefficient. And the plotted thing. And this particular pink line is reported by our group, where we have reported something like close to 0.8 at 650 Kelvin. And so then what is the how this thing we achieve? Now, whenever you prepare the material, make sure that your material should be highly dense. Sorry, irrespective of anything. So if you don't prepare a better sample, you will not be able to achieve the high jetting. People say that deliberately a porous sample is better, but when you make a porous sample, you compromise with the electrical resistivity or electrical conductivity. So that will not help. Always better you go to the achieving the density more than 95%, 99%, and then you will automatically, you will see that how this it will be improved. So this is again the basic property of a tetrahedrite. I will not read this slide. Let us, and these are all different group published data. Now let us look at it, how to improve the JT in this material. So I will, the other approaches are applicable for other material. So either you go for a substitution or doping in copper side or antimony side or sulfur side. Any side you go, and this material itself have a very high electrical conductivity. Our aim is to reduce the electrical conductivity. It is not a conventional thermoelectric research. It is a reverse way we have to treat this material. Sorry. The influence of a D-block transition metal, single substitution in the electronic property. So now let us look at all these different transition metal, how it is affecting the thermoelectric property. Now you look at, this is the periodic table, and this blue mark is the site for the substitution, that means the copper, and all this substituent material is in the red way. And what already people have published, many paper published in this JT of this, but there was no concise information that when when you substitute this material, why this JT is increase or decrease or why in this range, there was no proper explanation. So we started working on this, and we could find out the some meaningful conclusion about it. So these are the different material. This is by solid state method, and these are the XRD result, which shows that they are the polycrystalline in nature and contains a few minor impurity phase, because in this material you cannot always prepare a phase pure material. Always you will land up with some favorable other phase that will be there. And this is very important slide. You can see that the lattice parameter vary with the dopant, and you can see that the substituent radius, that when you this is the copper plus 1 and copper plus 2, that is the lattice parameter is here, and slowly you replace with the manganese, iron, cobalt, nickel, and zinc. But lattice parameter follows the trend ionic radius, except the iron, that is an exceptional case. Or that I will tell that later stage why it is coming. And so if he had a more covalent nature of a bond strength, decrease in the bond, increase the lattice parameter. That's why it did not follow it. Then we have checked the, though there are several impurity phases are there, we have done the thermal analysis to find out what are the possible phase and what is the decomposition of this material before doing the experiment. We noticed that for nickel, iron, and zinc substituted sample, so 650 there is a pump, and that is attributed to the covalent copper antimony sulfur phase. And for the nickel sample, there is a peak here at 850, which is nickel sulfide phase is there, and some other phase, and the sample is we stand up to 810K. After that, it starts decomposing. We have also checked the composition and microstructure of this material, and you could see that there are a large number of secondary phase. It is visible in the EPM microgram, and there are a different amount of secondary phase. It is present in that we have quantified from this experiment. Now the important fact is coming as what is the oxidation state we are retaining in this sample. Now in pure COSB, pure tetrahydride, so the copper is retaining +1, +2 oxidation state, antimony is +3, and sulfur is +2. So which is essential for the tetrahydride structure. But when we look at it, except iron, so all the transition metal behaves as a oxidation state of a +2. So that means, so we are substituting copper +1 oxidation state with the transition metal +2, so that the charge carrier compensation will be there. It will reduce the electrical conductivity, increase the electrical resistivity, so that the thermal conductivity will get decrease. That is what the whole idea. So we have done some theoretical calculation to find out the band structure of this material. So I will not go details about it, but just I will tell that this transition substitution created hybrid impurity level both within the valence band and the band gap, thereby modifying the band structure and altering the band degeneracy near the Fermi level. And only one of the important result what we found is the highest density of states and degeneracy near at Fermi energy was exhibited by the cobalt substituted sample, not the sample. So then we have gone for taking the UPS, ultraviolet photoelectron spectroscopy, and here you can find out to probe the work function of the material. And so these are a different calculation when we notice even cobalt substituted has a Fermi level position, that is the lowest Fermi level within respect to the vacuum level and high band degeneracy. So this was also consistent with the DFT calculation. And even one more step we have done is calculating the magnetic susceptibility and finding out the this parameter that gives you the indication that the density of states near the Fermi level, and this is you can see the covalent added substituted sample has chi0 high. So after that, I will skip this one. Then we have gone for the high temperature transport property measurement, and when you can see that the our initial aim was to reduce the carrier concentration by substituting the transition metal have a +2 oxidation state. So now this is your pure tetrahydride material, and after adding the or substituting the transition metal, the electrical resistivity increase. Electrical resistivity increase means it gives the idea about the carrier concentration decrease, or the uh, when the +2 oxidation state you are adding in a +1 oxidation state. So that is a carrier compensation is happening. So this is the information we got. And you look at the Seebeck coefficient also increase with different uh, substitute material. So that means it is reciprocate the electrical resistivity as electrical resistivity increase, Seebeck coefficient increase, because it is inversely related the carrier concentration with the Seebeck. So when carrier concentration decrease, the Seebeck coefficient increase. And you can look at the effective mass, and then we have calculated the power factor, and power factor shows that the cobalt substituted material shows the highest power factor that contribute to the other physics what I explained before. Now look at the total thermal conductivity. So total thermal conductivity uh, uh, it is decreased with substituting different element, but it is not a regular way it follows. But you can see that the material which the zinc has the highest electrical resistivity, highest Seebeck coefficient, has the lowest total thermal conductivity. So that means it is going towards the insulating one. And cobalt substituted one has in between some this material total thermal conductivity, and this total thermal conductivity also separated from the electronic part calculated relation. You can see that this is the lattice part of the thermal conductivity and this is the electronic part of the thermal conductivity, and the lattice part of thermal conductivity decrease for the cobalt substitute material. Now you can see that the thermoelectric figure of merit, which is plotted as a function of temperature for a different material, and maximum ZT has been reported for the cobalt substituted sample, and this is due to the high power factor, which is 1.76 milliwatt per meter Kelvin at 673 Kelvin, and this is because the reasonable low thermal conductivity, which is 1.2 watt per meter Kelvin at this. And uh, from this part, what we learn is, in general, the small concentration of a transition metal 1.7 to 3.4 atomic percent enable to optimize the compensation of hole and reduce overall thermal conductivity, beneficial for improving the thermoelectric property. This transition metal can cause the structural stability, and copper 2 atom, that is 12E side out of plane displacement, and degeneracy of the band of uh, this tetrahedride has been modified with the transition metal element, and because of the high band degeneracy in cobalt substituted sample was confirmed by the DFT calculation, which was also indicated by this high density of state as near Fermi energy, confirmed by the magnetic susceptibility data and UPS data. A coherent explanation was thus given behind the high figure of merit in cobalt substituted sample based on the theoretical calculation and experimental result. And the analysis and the substitution can apply for other ternary compounds with similar band structure. So this is one part of the story. Then the other part is the material that has been substituted by tin. Tin has a very peculiar characteristic. It has a +2 and +4 oxidation state. But when we initially did our experiment, we never thought that it is a +4. We thought that it is a +2 like other transition element. But some interesting fact it came out with a different doing the experiment that I will explain now. So this tin will also increase the anharmonicity. So this anharmonicity is responsible for the low thermal conductivity. And tin and antimony mass difference can scatter the phonon and it can reduce the lattice part of thermal conductivity. But tin double substitution in copper 2 side and antimony side was observed, and hence detailed study was done. I will not. Here this is very interesting thing. Now you can see that this is again polycrystalline material, and which has contains so many impurity B. But we have carried out the rate analysis, and remember that rate analysis means anything you can put it at any side, but you have to be carefully observe that how which way it is this material is going. So now this tin was substituted at different sites. So when tin was substituted as copper 1, that is 12D side, this is the Bragg factor and this is chi-square. When it is 12E side, this is the thing. And when it is only antimony side, 8C side, this is the result. And then what we did is we substituted tin in both copper 12D side and antimony 8C side, copper 12E side, antimony side. And you can see that the best result we got in copper 12E side and antimony 8C side. Similarly, this was also the other sample also. This is the thing. So that means, so putting the tin, it is always a double substitution. It is substitute copper 12E and antimony 8C side. So these are the experimental result that relative analysis has been carried out, and you can see that the lattice parameter increase with increase in tin content, and the explanation for that is the whether it is a tin is in +4 oxidation state or it is a +2 oxidation state. The ionic radii of this thing is larger than copper +1 or copper +2 or antimony +3. So that's why the logic is fit well as the tin content increase with increase in lattice parameter. And similarly, we have estimated the composition of each phase, and also we find out the impurity phase percentage present in the sample. Then after that, this is very important. Then we have done the XPS experiment to find out whether really the tin is present in both oxidation state or it is a single oxidation state. But it was not so surprised that tin was both present in plus oxidation state and +2 oxidation state and +4 oxidation state in all the samples. So the peak correspond to +2, +4 oxidation stage has a high intensity and +2 oxidation stage has a low intensity, that one. And this was also confirmed by both XRD, EPM and DFT result also agree with this. So what we did is again, these are the DFT calculation. So we have started doing the DFT calculation considering that adding the tin in copper 1 side, copper 2 side, antimony side, both copper 12 side, antimony 8C side, and copper 1 side and antimony 8C side. But the to find out the best result, the tin is either copper 12D side uh, or it is in the mixed way, and which is having +4 oxidation state, and tin which was replaced by the antimony side that is in +2 oxidation state. So this was also confirmed with this um, DFT calculation. But still, when we are claiming that the tin has a both oxidation state and replacing copper 2 as well as antimony, so this has to be any reviewer also asked some more strong proof is required to accept this paper. Then we have done sorry, mass balance spectroscopy, which gives again the confirmation that, so you can see that this isomer shift, that is delta from 0.55 to 0.58, that refers to oxidation state of a +4. So that means here also we confirm that tin is present in +4 oxidation state, and the other this quadruple splitting, that is 0.981 mm per second, that reflect the SN is also fourth coordination number. And when you look at the low quadruple splitting value, the tin is also having +2 oxidation state. So overall, all this, whether it is XPS, XRD, EPML, or DFT calculation or Mossberg spectroscopy. Everywhere we prove that tin is having +2 and +4 oxidation state, and tin is replacing +4 with copper 12 E side and antimony 8C side. Then we have carried out all the transport property measurement, and you can see that this is your low tin substituted sample, and when you are adding the tin more and more, then the electrical resistivity going up. That means more number of charge carriers are getting compensated, and it is going towards the insulating one. But this is a very systematic one. So the higher row that has been indicated that effective compensation of a hole, and the row increase with increase in X and increase quantity, and you can see that it is because of the copper 2 position and antimony 8C position. But if you look at the Seaborg coefficient, it is not following. Like in the first part, whatever I explained, that when the charge carrier reduce, then the Seaborg coefficient will be more. But here it is not the same case. Here you could see that which has a high electrical resistivity has a low Seaborg coefficient, which is contradictory here. And for that, that is the interesting physics is behind it. So you can look at it. The Seaborg coefficient is, yeah, it is inversely related to the charge carrier concentration. At the same time, the first term also contains dE by dN. So d by dE by n. So this term also create some contribution here. The second part is also contains the mobility, which is 1 by mu, which is related to Seaborg coefficient, and the other part is it contains d mu by dE. So that means you cannot just like it only one type of a carrier, one place it is replacing. You can say whether it is this increase Seaborg electrical resistivity, Seaborg coefficient will increase. But here what is happening? First of all, this is a double substitution. One is it is in the copper side it is substituting. It is in the antimony side it is substituting, and the mechanism for copper side and antimony side is completely different. And these are the term which also make things much more complicated one. So that's why the complex function of the scale and the it depends on the density of state effective mass near it, and all these complicated things could not explain that whether it's increase or decrease. So this is the information one has to be careful. And then you can calculate the power factor, which is here it is highest power factor with the lowest tin filler or substituted sample, and this is the total thermal conductivity. Total thermal conductivity is uh, 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 low for the 0.25 and 0.35 substituted sample. You can see that the electronic part has been separated from the total thermal conductivity, and this is the lattice part thermal conductivity. And sorry, you can see that the highest ZT has been reported with the 0.25 or 0.35. That is something like 0.96 at 673 Kelvin. And this is happening due to the suppressed total thermal conductivity, which is 0.88 watt per meter Kelvin, which is very low because it is happening of a double substitution, and ZT of one of the highest among single and double substituted tetrahedride. And the significant enhance of ZT can be attended in a tetrahedride with a small concentration less than 0.5 per formula cell with a double occupancy of a copper 2 position and antimony side. And this has a compatibility factor which is not I will conclude here that uh, the tin has an interesting property of existing mix balancing clause 4 and clause 2 and substituting at copper 12 E side and antimony HC side. And this copper 2 side compensate hole and moves the Fermi level towards the band gap, whereas tin at antimony side introduce the hole state near the Fermi level. A trade-off between these two effects determine the overall transport property, and total thermal conductivity of substituted sample could be reduced primarily due to reduction in K electronic part and the maximum ZT of 0.96 that has been achieved or 0.35 sample, and this double substituted scenario could be achieved using only one kind of substitution, and which also facilitated the cost effective material preparation and coupled with a favorable compatible factor, and that this opens the idea that even people can think about going for a double substitution in a tetrahedride material in some other material to improve the thermoelectric property. So thank you very much for your attention. Let me thank all the funding agency, DST, ISRO, IIC, generously for funding, supporting our research, and all my collaborators in India and abroad, Professor Rogel, Austria, Professor Eckhard Miller in Germany, Professor Kim in South Korea, Professor Manish Jain in Physics Department, Professor Satyam Swas in Material Engineering, and Professor Sistov in KGH Poland, and all my former students who really work hard and achieve this result. So thank you very much for your patience listening to me. Now, if you have any question, please feel free to ask me. Thank you.
Thank you very much, Professor Malik, for your informative talk regarding thermoelectric materials. This is now this time for the participants' questions. If you have any questions, then please ask Professor for your query and suggestions. Thank you very much. Please. Any questions? I think there is no more questions. So I conclude this talk. This and is ended for the next session. So thank you very much, Professor Malik, for your informative talk. Thank you very much.
Thank you.
So our last talk of our today lecture is from Dr. Arindam Biswas. So this lecture will start 2 o'clock. So for these things, so now it is a coffee time. Please enjoy.